Okay, so we're going to kind of continue our work on derivatives. And essentially at this point, I mean, you have the power rule, the product rule, the quotient rule, the chain rule. We did derivatives of trig functions. We know we can now throw all of these things together and give some really complex type functions to work with. But as long as you apply the rules correctly, go step by step, the derivatives are actually relatively easy to find. There are a few other types of functions that we've mentioned that we haven't found derivatives for yet, and that's what we're going to be doing. But in order to do that, we need another type of algebraic trick that will also allow us to solve some complex applications that we're going to do at the end of this chapter. So I wanted to go through that trick now, but the trick is actually based off of stuff we've already done. Meaning, suppose I have y equals 3x plus 5, maybe 3x squared just for fun, cubed. If I want to find the derivative, well, we know now I'm not going to FOIL that thing out 3 times. I'm just going to use the chain rule. So I'll get y prime equals, let's see, bring down the 3. The inside function stays the same. Lower the power by 1. And then I multiply by the derivative of the inside, which will be 6x. And there we go. And as far as it goes from a math perspective, this is called an explicit function, meaning y equals, and I tell you what the function is. But for the sake of argument, what if I didn't tell you what that function was? Like before, when we actually defined the chain rule, I think we just had something like y equals f of g of x, some arbitrary function. But then we said, well, the derivative, you take the derivative of the outside function, the inside thing, whatever it is, stays the same, and then you multiply by the derivative of the inside thing right there. So if I maybe didn't actually tell you what this function was on the inside, and instead I just said, well, y equals, different than this, maybe I'll say y equals f of x cubed. Could I actually get the derivative of that? Well, yeah, I actually could. I could say y prime is equal to, chain rule still applies, this is still a composition of functions, bring down the 3, the inside function stays the same, lower the power by 1, and then the chain rule just says, take the derivative of the inside. And now, admittedly, I don't actually know fully what the derivative looks like because I have this f of x and f prime of x, which are implicit. I don't know what they are, but I can still say that's the derivative right there. And that's kind of the trick we want to work on and expand a little bit. It's actually called implicit differentiation. And the idea is, well, we've done explicit functions. I give you the function, you tell me the derivative. What if I don't tell you the function and I only give you an implicit function, f or g or y? Can you still find the derivative of it? Well, yeah, as long as you apply the chain rule. Suppose we have this. All of you in 171 or 172 did circles. X squared plus y squared equals, we'll say, 25. It's the equation of a circle centered at the origin of radius 5. If I quickly sketch a graph, and again, I'm not going to be incredibly detailed on my graph. It's a circle that looks like that. Maybe we'll label points in a minute. Well, could I get the derivative of that right there? Now, keep in mind, that is not a function. We all know circles are not functions, vertical line test, blah, 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 blah. But clearly, I can certainly get a whole lot of tangent lines. I mean, there's a tangent line there and there. I could do tangent lines at the top and bottom. I could do tangent lines at the left and the right. Here I get 0 slope tangent lines. That's undefined. This would be undefined. Here the slope of the tangent line is negative. Here it's positive. So clearly there are a lot of tangent lines there, and I'd like to be able to find them, to find the rate of change as you go around the circle. When is it increasing, decreasing, negative, 0, undefined? So I want to be able to find the derivative of that. all I really need to do is apply my derivative rules, understanding that x is a variable, just like before. So I just apply my derivative rules, power rule, product rule, quotient rule, just like before. But y is a function, because we define y as a function. So this I'm going to have to treat as an implicit function squared. You can call it f of x squared if you want. And then use the chain rule trick. So let's see. The derivative of x squared, that's just the power rule, that's 2x, plus the derivative of y squared. Again, chain rule says that's a function squared. So I bring down the 2. The inside function stays the same. I lower the power by 1. And then I multiply by the derivative of the inside. The derivative of y is y prime. Equals the derivative of 25. 25 is a constant, so the derivative is 0. And now I have this complex expression for my derivative, but ultimately my derivative that I care about for this is y prime. And I can algebraically solve for it right here. So subtract the 2x, divide the 2y, and I'll get y prime equals negative 2x all over 2y, which reduces to negative x over y. And now this essentially says that y prime, my derivative for the circle, is negative x over y. If you think about it, it makes sense. To find the slope of the tangent line for any point on this circle, clearly that derivative should be based off of both the x value, is it positive or negative, and the y value, is it positive or negative. So it's logical that my derivative should incorporate both x's and y's. And just to test it really quick, suppose I find, since I have the circle right here, suppose I want to find y prime of, we need a point xy, so I'll pick the point 0, 5. That's the point at the top of the circle, 0, 5, that gives me 25, and I'm good. But if I plug that in here, I get y prime of 0, 5 is equal to negative x is 0, y is 5, and that doesn't matter because it's over 0, so I get 0. Which is exactly what I should get. At the top of the circle at the point 0, 5, my slope is horizontal. So I get a slope of 0. It makes sense. If I arbitrarily pick a point here, I'll just pick a point in the first quadrant. 3, 4. 3 squared is 9, 4 squared is 16, 9 and 16 is 25. So I can do y prime of 3, 4. If I plug that in here, I get negative 3 over 4, which means the slope of my tangent line, my derivative is negative. It should be negative. Here the tangent lines go down. By extension, if I did y prime of, I didn't need the equals right there, y prime of, we'll do 3, negative 4, which is the point down here in the fourth quadrant, well then I'll just get negative 3 over negative 4, which is 3/4, and my slope is positive, which again, it should be. So clearly, this idea of implicit differentiation allows us to find the derivatives, the rates of change, of things that aren't actually functions as we define them. We just have to keep this implicit trick in mind. Anytime I see an x, I just apply my derivatives like normal. Anytime I see a y, I apply a chain rule to it. So, we're going to do a few more examples of this, because this is actually really important. I also find it really entertaining myself, so I like doing these. Suppose I have x squared plus 2xy plus y squared equals 7. Find dy dx. And one thing I will point out, we've said repeatedly, you should understand derivatives both from the y prime way of writing it, the f of x, f prime of x way of writing it, and the dy dx Leibniz notation. And a lot of times you'll see Leibniz notation for this implicit differentiation. It occurs in other places, but a lot of times here for the implicit differentiation. So find dy dx. First, take the derivative of everything. Just go term by term. The derivative of x squared is 2x. Not a big deal, power rule. Here, this is where students tend to sometimes have trouble. That is a product. It's 2x times y. So I have to apply the product rule. Product rule says the first, 2x, times the derivative of the second. The derivative of the function y is just y prime, plus the second, which is y, times the derivative of the first. The derivative of 2x is 2, power rule. Now this is my product rule, worked out, so now I'm good with that. Now I move to the next term. Y squared, that's a chain rule. I bring down the 2. The inside y function stays the same. I lower the power by 1, so it's 1 now, times the derivative of the inside, which is dy dx. The derivative of y equals the derivative of 7, the constant, is 0. And now I just solved this out, and here I used y prime to abbreviate it, but y prime is dy dx. You can use either notation. If you prefer one over the other, you can just find y prime as opposed to dy dx. I just want you to see all the different ways to write this. But now this is just an algebra question. I want to isolate the dy dx, so I'll keep those on the left. 2x dy dx plus 2y dy dx equals, get rid of the other things, minus 2x minus 2y. Bring those to the right. Now here, isolate the dy dx, so factor out the 2x plus 2y. So I get dy dx times 2x plus 2y equals minus 2x minus 2y. Now, solve for dy dx. dy dx, just divide that. I get minus 2x minus 2y all over 2x plus 2y. And now, in this case, I'm actually going to do a trick. I'm going to factor a negative 2 out of the top, which will leave me with x plus y, and a 2 out of the bottom, which will leave me with x plus y. Those will cancel, the 2's will cancel, and as it turns out, dy dx is just negative 1. Sometimes they're messy, sometimes they're not. But the point is, you just keep applying your derivative rules over and over and over again, making sure to account, remember, when you have a variable, when you have a product, when you have a function, and applying the rules correctly. I'm going to end this video now because it's already at like 13 minutes, but I'm going to make another video going through a few more examples so you can see them worked out.